So for this video, we're going to look at the location of the particle. So just to review all of the rules that we're going to have, all the rules in quantum mechanics are right here. Just to remind you, what do we say? The states are normalized vectors. This dot product between two states is the probability amplitude, and when you squared it, it became the probability of measuring state A if you were in state B. The third one was for every observable, there's an associated operator, and we put the little caret on top of it. The fourth one was our eigenvector eigenvalue. Anytime we operate on our state, we get the possible values back on our state. So normally, for a specific operator, you get back what you measure and the eigenfunctions that come with it. And then we said this rule right here is probably more of a statistical rule. We said the average or expectation value you get from many measurements of identical systems is given by, you put it a sandwich in here between the operator, and we designate it like this. And this is the average, and the standard deviation of that average is given by this right here. It's the operator, it's the average of the operator square minus the square of the operator. So the square's inside here, the square's outside. And then the last rule right here, when we operate the energy operator, this is the Hamiltonian on our state, this is how it changes with time. So that was all of our quantum rules that we're going to have right here. So now what do we want to do? Well, everything we were working on before was up, down. So it was a two-state system. It was like the flip of a coin, heads or tails. Now, we don't really care about whether the coin is a head or a tail. We care about where is the coin. And then later, we'll bring back the heads or the tails later. But right now, all we care about is where is the particle. And just to start out simple, we'll assume it's in a straight line, say in the x direction. So we'll just start out one dimension. So not only that, we'll make it the x direction. We'll even limit it on the x direction. How about if we say the particle is somewhere between 0 and 1. So x is somewhere less than 1, greater than 0. But we could have extended it, but well, let's just pick it between these two right here. So now we ask, what are the states of the system? Well, the states of the system is everything you can measure. Well, we could say the particle could be right there. 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 Okay, the particle could be, let me just pick one, and maybe right there. It could be right there, which is, let's say, 0.3862 ... There's some real value that it could have right there. Well, what should we call that state? Well, I guess I could call it, I can't call it up and I can't call it down. I guess for that one right there, I could call it, say, psi, I don't want to call it 1 or 2. How about 0.3862 ... Maybe that's what I'll call that state right there. And maybe I have another state out here. Come out a little bit further. Maybe this guy out here. Maybe that's, say, 0.8514 ... And we can call that state right there psi of 0.8514 ... Okay, so it looks like it could be any of these values right here. And remember, just like with our two-state system, we could say you could be up or you could be down. And so then you could be a combination. You could be alpha up plus beta down. Well, here we're a combination of all of these. So our general state psi, in this case, would be the first one right there, alpha, and then the very first psi, I guess, would be psi of, I guess, the very first number. It can't be 0 because I said greater than 0. 0.0000 ... 1. Forever, 1. But I don't want to call this alpha 1 because I'll run out of alphas right here. How about if I just give it the same subscript I give that one? 0.000 ... 1. Okay, and then we've got the next one. The next one up here, which would have been alpha of 0.0000 ... 2. Psi of 0.0000 ... 2. Plus the next one, plus the next one, plus ... And the very last one, I guess, would be the one way out there on the end, which would be alpha of 0.9999 ... psi of 0.9999 ... Okay, a lot of dots right here. Okay, so this would be the state of the system right here, where this squared would be the probability, this times its complex conjugate would be the probability of measuring it at 0.00001. This squared would be the probability of measuring it at that location. And you keep going up. And if I added these all up, that is alpha of 0.0000 ... 1, sorry, 1 squared plus alpha 0.0000 ... 2 squared plus all the way out to the last one, 0.999 alpha. 0.9999 squared, that should equal 1. Okay, well, and these would be the eigenfunctions, really. They would be our eigenfunctions. If we want, and these guys would all be orthonormal to each other. If I wanted to guess what these would look like, I could probably guess what this one looks like, this first one. Psi of 0.000 ... 1. It's a column, remember, and the number of items is the dimensions. Well, it's got an infinite, there's an infinite number of them between 0 and 1, but this one would just be 1, and then the rest would be 0, all the way down. This one right here, psi of 0.00002 would be 0, 1, 0, all the way down. And the last one down here, this psi 0.9999 would equal 0, 0, 0, the last one would be 1. And you can see if I dot any of these two with any one with another one, you're going to get 0. And if I dotted it with itself, I would get 1. So for any psi at any x value I have in here, if I dotted that, if I did any psi of x with psi of y, where x and y are just two of these values, you would get 1 when x equals y, and you get 0 when x is not equal to y. Again, that's our orthonormality. And again, I guess a shorthand notation, I guess I could write it like this, right there. So it's 1 when they're equal, 0 when they're not equal. Okay, so this right here, I could probably write that a little bit shorter notation. Couldn't I write this as a sum right there? So we could write psi as, I'm just summing up, sum of alpha sub x psi of x, alpha of x psi of x, okay, where x is going from 0 to 1, but not in integers. So this is, x, actually it's going from not quite 0, it's going, how about if we just say x is less than, is between 0 and 1, where x is an element of all the reals, I guess. I don't know if this is kosher, but you know what I'm talking about right here. It means we're adding up all of the real numbers in this sum from everything greater than 0 and less than 1, right there. Okay, well, that's what the state would be in right here. This looks like a very cumbersome way of writing things right here. We're going to get away from this right here. Suppose I asked, what is the probability amplitude of measuring it right there, right at this location, right there? Well, we just come back to our rules right here. The probability amplitude is, if you're starting out in the state psi, and you ask, what is the probability that I'm going to measure psi of 0.3862? Psi of 0.3862 ... right there. Well, then what do? I'll just plug this into here. And so we get psi of 0.3862 ... And then for this, I'm going to put in this sum. This sum, x is between 0 and 1, where x is an element of all the reals, of alpha sub x, psi of x. Okay, well, I can pull out the sum. This one isn't changing. This is a constant. So I'm going to pull this out in front of here and even pull my alpha sub x's out. So this right here is the sum of x between 1 and 0. X is an element of all the reals. And we're going to get alpha sub x. And then we've got this and that dotted together. Psi of 0.3862 ... psi of x. Okay. So what are we going to do? We're going to, remember, psi of x was all of this stuff right here. So you notice when we start dotting these two, almost every single sum is 0 right here. The only time they're not 0 is when these two are the same. So when you come over here and you start putting in the 0.0001, that's going to be 0. The only time this is going to be non-zero is when x is equal to that number. And then you'll get 1. So this becomes just 1, and that x becomes that 0.3862 right here. So this is just alpha of 0.3862, 0.3862 ... But we already knew that. We had gotten it from right here. The probability of finding it there is this. So the probability amplitude is just the alphas. So the alphas, these alphas are just the probability amplitude. Now, what if I didn't say, what if I said for a particular, here I just said for a particular value of 0.386. What if we said, what is the probability of finding it at any location of x? So if I just asked, not for 0.386, but just any value of x. For any value of x, and I dot that with my psi. Right there. What would that be? That would be the probability amplitude of finding it at a specific location given this right here. Well, we know what it's going to be because because we did it when this was 0.3862. It came out to be alpha of 0.3862. And if I put whatever number I put there, that's going to just be that same alpha, alpha of x. So these are just the probability amplitudes of finding it at each location right here. Now we're going to give a name to this right here. We're actually going to give this, you know, since this is like more or less a continuous value, you've got an infinite number of these alphas. They're at every single real number right there. We could almost think of this as a function. And we're going to give it a name. We're going to call it, it's a function of x. It could even be a function of time, because this is the probability amplitude of finding the particle. He might be moving. So maybe we'll just put the time in there right here. And we're going to give a name to that. We're going to call it the wave function. Now the book starts out in quantum with the wave function, but they never really said where it came from. Right here. Well, this is where it's coming from. So what you're looking at is so anytime we bring up the function, so now we're not in vectors anymore, and we're not in column vectors. We're going to just use function. That way we don't have to deal with an infinite number of them. They're so continuous that everything is just a function. So now if we were to plot out the alpha everywhere along here, you know, if I could, let's just say don't worry about whether it's real or complex, but the alphas, you're going to get alphas at every location right here. And that would be kind of the wave function. It's just the probability of amplitude of finding the particle at a particular value of x. So this is now what we're going to use. We won't use states anymore. So our rules are going to change a little bit. We have to modify our rules so they work with the wave function right here. Okay, so what are our new rules going to be then? What are these new rules? They're just going to be modified a little bit to deal with wave functions. So the first one is, just like we had up there, the states of the system were normalized vectors. Here, we're just going to say psi of x and t, psi, it's big psi, x and t, which we define as the probability amplitude, for finding the particle at location x, at location x. It might be at a certain time t, but let's just not worry about the time part right now. Okay, so that's what we're going to be using. It's just, so anytime you see a psi, always think of it, it's the probability amplitude. It's not the probability. Remember, to get it to turn into the probability, I guess we'll use the second one right here. How did we get the probability from the probability amplitude? We took the square of it right there. So that'll be my second rule right here. If I multiply this by its complex conjugate, psi star of x and t, psi of x and t, or if I want to write it like this, psi of x and t squared, that's the probability. Probability of finding the particle at location x and at time t, but let's not worry about that, at location x, at location x. Okay, so now we have some way of, if we can get this wave function, we can get the probability of where it's going to be at any location of x. Now, we said before that all of our vectors were normalized. That is, when we dotted two vectors that were the same, we always got one. Well, it's similar here. If this is the probability of finding it at location x, the probability of finding it here, plus the probability there, plus the probability there, all the way out to here, better be 1, because it has to be someplace. And so if you search everywhere, the probability of finding it should be 1. So, and, maybe I'll put and, it's part of this rule number 2. And if I sum this thing up, remember this is an infinite sum, so it's an integral. The integral of psi of x and t at a particular time, star psi of x t, integrating everywhere, I'll just say minus infinity to infinity, but for this case it would just be from 0 to 1, dx should always equals 1. That's going to be my normalization. So we have to normalize these wave functions, just like we had to have normalized states before. These are going to be normalized. So this is our normalization. Normalization. Okay, so we've got that right there. Okay, well, let's look at the next rule right here. For every observable, there's an operator. That stays the same. Okay, so observable you get an operator. Okay, so that's not going to change right here. Okay, let me just erase this thing right here. Now number 4. What else did we have down here? When we operate on the state, we get lambda times our function back again, our state. But I guess I'll write it right here. Maybe I'll write it up here and come back to there. When we operated on our state psi, we got our lambda times state psi. Well, what if we just replaced our psi? What if we just did psi x to both sides, psi x to both sides? Did it to both sides. If we did it to both sides, right here, just throw that in there. This just becomes our wave function, because this was our wave function and that would become our wave function. So this rule is going to still be the same. It's just that now it's not on our state, it's on our wave function. Equals lambda times back our wave function, x and t. So now, but what we had before is, this was a vector, and our operators were matrices. But now this is a function, and so our operators won't be matrices, they'll be something you can operate on a function, right here, which we'll show you some of them later on, right here. And remember, what this thing gives me is, it gives me a bunch of lambdas. Lambda 1, lambda 2, ... And those would be the eigenvalues, whatever you'd measure from this operator, and you would get these states. Psi 1 of x and t, psi 2 of x and t, ... And what did we say? We said before we made the measurement, we were a combination of all of those. So before we make the measurement, you're kind of a linear combination of them. You're the sum of alpha. How about if I just write alpha 1 psi 1 of x and t plus alpha 2 psi 2 of x and t plus dot, 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 dot. Where this squared would be the probability of getting psi 1, this squared is the probability of getting pi 2, kind of like we've been doing all along. But once you make, let's say you measure lambda 2, then all of this collapses down to psi 2, just like we did before. When we were in alpha up plus beta down, if we operated on it and we got 1/2 h bar, it collapsed to just up. So this is just the same thing. We're doing that right there. And these guys were all going to be orthonormal. That is, if I dot these two, when you're dotting, this is kind of like a dot product right here, because what do you do with a dot product? You multiply their i's components together, you multiply their j's and add them up. Except here we have an infinite sum since there's so many terms right here. And so if you integrate this times this, you're always going to get 1 when they're equal, 0 when they're not equal. Okay, so the rules aren't that much different. They're just now this thing right here, the average value right here. Instead of these vectors right here, we're dotting this and we're putting the operator in the middle. So now we get the average value, we call that, I guess, 5. The average value of an operator is now going to be the integral of psi star, and then you put the operator in between. Remember, it acts on functions psi dx. And again, you're integrating over wherever it could be, right there. So that's what it's going to be. Remember, before it was like a sandwich. It still is a sandwich, but now it's written as a function rather than as a vector. Okay, this rule isn't going to change at all. It's just that you use the ones that you got from there. So this is still the same. So I might as well write that down. And this is the average, and then the uncertainty in that operator is equal to the square root of the average of the operator squared minus the operator squared. Okay, that still stays the same. And then the last one down there is H6. H. Well, if I just put in turn all these guys, all they're going to do again is just turn into our functions. They were vectors, now they're an infinite dimensional, but they're pretty much a function. That's just going to become our wave function. So we've got h on psi of x and t equals I h bar. But since psi is a function of both x and t, I have to turn this into a partial derivative right here, since there's an x and a t in there. So this is my h bar partial, because I only want to take the derivative with respect to time right here, of x and t with respect to time. Okay, so those are all of our rules. We're not going to have anything new to it. All we did was, before we were working on vectors, now we're going to be working on what we call wave functions, which is the probability amplitude of finding it at a particular value of x. Now, let's just look at some of these operators right here. So we could give it the name of the operator. Maybe you wanted to measure the position. Position right here. We'll just say use an x for the I guess that'll be the label. And then what do you do to the function right here? If you wanted to measure the average x position, you would throw in there just so the operator, you just put an x there. That's all you do. You just throw an x in there. What if you wanted to measure the position squared? Position squared. squared. I guess I'll write it like that. This would be like that right there. Well, what do I do in there? I plug in x squared. What about any function of x? Any function right here. F of x. I guess I could write that as f of x, like that. You would just plug in that f of x right there. Or what about the potential energy? The potential energy on a one-dimensional is just a function of x. So if you were in the potential energy, u of x, you would do, it's just a function of x. You would just throw in u of x right there. U of x. You'll notice that if I wanted to find the uncertainty in the position, I would need the operator x squared and x. And so I would need to do both of these two right here, because I need the average of x squared and I need the average of x, and then square it and take the difference and so on. Well, what about momentum? Momentum right here. We can call it, say, p. In this case, it's just p and the x's is all one dimension right here. But we don't put mv over there. For momentum, remember, momentum and position have strange relationship in quantum mechanics. This one is just minus I h bar partial with respect to x. So if I wanted to find the average momentum, right in there, that's why you can't put it here or there, it's got to be right in the middle. You just throw in a minus I h bar partial with respect to x. So the only thing you're taking the derivative of is that second one. Okay, well, what about kinetic energy? Kinetic energy. Remember, the definition of kinetic energy, at least classically, non-relativistically, it's just p squared over 2m. That was our definition of kinetic energy. So this would be the kinetic, I'll just write it as k right there. But what would the operator be? Well, I'd have to operate, I could write it like this. It's equal to p times p operator times p operator all over 2m. That would be p squared over 2m. Or plug in what this is. This first one would be minus I h bar partial with respect to x of the second one, which is another minus I h bar partial with respect to x all over 2m. Well, if we simplify this, minus I times minus I is minus 1. H bar squared all over 2m. And then the derivative with respect to x of the derivative with respect to x is the second derivative with respect to x squared. So there is the kinetic energy right there. Okay, what about the total energy? We need it because that's what H is. H is the total energy, and all we have is kinetic and potential, so it's just the kinetic energy plus the potential energy. So we'll just use the letter H for it. And what's the operator going to be? It's just going to be the sum of the potential and it's just the sum of these two right here. So it's going to be minus h bar squared all over 2m, second derivative with respect to x squared, plus u of x. So there is what we call the Hamiltonian operator right there. Okay, so now we can go in and we can put it in for this, because now we know what the Hamiltonian is right there. So I'm going to plug all of this right into here. So what do we have? So this equation right here becomes minus h bar squared over 2m times the second derivative of psi with respect to x squared, second derivative of psi of x and t with respect to x squared. So we've already put the psi in here, and then we got plus u of x times psi of x, because all of this goes right there. So you also got plus u of x psi of x and t. So that's what this left side, that's what I get when I operate h on psi. So I just put the psi there and the psi there. And then that equals the right side, equals I h bar partial psi of x and t with respect to t. Okay, so this equation right here is called Schrodinger's time-dependent equation in one dimension. Equation in one dimension. Okay, so it's more or less just an energy. It's just, all this is saying is the kinetic plus the potential is the total energy. That's really all you're saying. And what this does is, remember, this is kind of a probability amplitude of finding where the particle is. And this just tells you how that probability amplitude moves around as a function of space. And this tells you how it moves around as a function of time. And this is governed by the forces on it, right? Because the potential energy is related to the forces on it right now. Okay, so this is Schrodinger's time-dependent equation right here. You notice this is a partial differential equation, and it's actually complex because we got the I in there too. We'll see how to solve it in the next lecture. And I just wanted to say how, when you're putting in the potential, if we look at something, let's look at a simple a mass on a spring. If we look at a mass on a, well, let me put them down below. We have a mass on a spring here, tied down, and here's the equilibrium, and it's going back and forth right here on a frictionless surface. We know what the potential energy looks like. It looks like 1/2 kx squared. If I were to plot it here, this is x and this is u of x. We know what the potential energy is. It looks like this. U is equal to 1/2 kx squared. That was our, and so that's a plot of the potential energy of this system right here. Now suppose we built a bowl-shaped surface right here. This is some sort of a valley, frictionless valley, and let's say we put a block on this valley. We just set it right there on a frictionless surface. If we just set it there, what's it going to do? It's going to start to take off this way, right here. Pick up some speed. When it got down to here, it has a lot of speed, so it would go back up the other side. And since there's no friction, it would probably go up to the same height over here, and then it just go back and forth. Now, if we had a light source, let's say a light source up here shining down, and let's say this is a clear valley, you can see through to see our block down here, we would notice that as the light came down through here, if the block was here and this was here at the same time, they would both move back and forth together. That is, the x value of this block would have exactly matched the x value of that. And from classical mechanics, we know that the force is the minus the slope of that. It's actually minus the derivative of u with respect to x. You notice the slope is positive. The force in the x direction is negative. The force is in that direction. And the steeper this gets, the larger the force is in that direction. We know if we take the derivative of this, we just get minus kx, which is Hooke's law. And when you got over here, when it's somehow sliding along this way, the force would be in that. That's why it's slowing down right here. And when it got to the bottom, the slope is 0. So there is no horizontal force on it. It's right there. That's the equilibrium position. So here we're going to look at containing a particle by a potential well. We don't use forces because we can't poke away very easily. Remember, it's just kind of some sort of a wave. You don't want to be poked. But you can confine it into like a well right there. And that's exactly like this thing right here. Just like this is contained right here. So when we put in whatever the forces are, that's what's going to determine this right here. And once you put in that, you can get everything else. That's what's going to be put into it. Okay, so we'll continue on this, and we'll start with this and say, how do we solve this right here? Okay.